In this video, I'm going to go through the process of solving a system of equations using Gauss-Jordan reduction. This is an algorithm that will allow us to apply a sequence of elementary operations to our system that doesn't change the solution set, so it transforms our system to other equivalent systems, and it will be an algorithm that allows us to know exactly what we need to do at each step to take our system, transform it into a system that we know how to solve, and then we'll be able to write down the solution. This video is a bit long because I'm walking through this entire problem step by step. I always recommend with these problem videos, if you're only stuck on one part of the process, please skip ahead to that part. So for instance, if you know how to do the forward direction, but you don't know how to do the backward direction, whatever that means, we'll find out in this video, you would maybe skip ahead to the part where I'm doing the backward direction so that you're not watching, a 20-minute video or whatever this turns out to be in the end. All right, so I'm going to walk through kind of two things side by side. I'm going to walk through the process of solving this system, and then beneath that, I have this Word document that goes through what we're trying to do in general, right? I'm working on the top on a specific problem, and the Word document is the general process that we're trying to do. I'll put a link to this document in the video description so that you can look at it on your own if you want. So here we have a system of equations. 6x2 plus 18x3 plus 12x4 equals 0, minus 2x1 plus 10x2 minus 16x3 plus 2x4 equals minus 14, and 3x1 minus 19x2 plus 12x3 minus 8x4 equals 18. And you might look at this and think of several things that you could do, several operations that could make this simpler. Maybe you look at it and you say, hey, this first equation, everything's divisible by 6. The second equation, everything's divisible by 2. Where do we start? What do we do first? And that's the whole idea of this process. So this overview of Gauss-Jordan reduction, let's start with step 1 right now. The first thing we're going to do is we're going to convert our system into an augmented matrix. So what does that mean? Well, we're going to get rid of all of the superfluous stuff that would appear every time. We don't need to write down x1 each time. We don't need to write down these equal signs each time. So we'll convert this to an augmented matrix. So as an augmented matrix, this thing looks like this. I always like to write a vertical line here in order to separate out the left-hand side coefficients from the right-hand side coefficients. And I put brackets on the outside of this matrix. There are lots of different ways to write matrices. I'm trying to use brackets to be consistent, but parentheses would be fine as well. So we've converted this to an augmented matrix. Maybe the one real thing to point out, all these numbers look the same. We didn't have an x1. That's the same as 0x1. We need to keep track of our zeros. We can't just leave this blank. All right, so that's step 1. We convert to an augmented matrix. Now, step 2 is going to be this big sequence. We're going to convert this augmented matrix to what's known as reduced row echelon form. This is the main part of the process. And there's going to be, we'll see what that is once we get there. It's not worth defining what reduced row echelon form is right away without seeing an example. But what we're going to do is we're going to do a sequence of elementary row operations on this matrix in order to transform it into reduced row echelon form. So we'll either switch two rows, we'll multiply a row by a non-zero constant, or we'll add a multiple of one row to another row. And we'll never do more than one of these at the same time. At the end of the video, I'll address there are rare situations when you can do more than one row operation at the same time, but it's really important that we go one at a time so that we know that our resulting system, after applying the operation, is equivalent to the original system. Otherwise, we won't know that. We won't know that we haven't gotten rid of or introduced new solutions. Okay, so this is the meat of the algorithm, is applying this series of row operations. And then once we're done, we'll have a matrix in reduced row echelon form that is relatively straightforward to solve once we convert it back into a system of equations. All right, so the first part of the process is to take this matrix and turn it into just echelon form, not reduced row echelon form. And this is what's known as the forward direction of the process. So let's scroll down to look at this. Forward direction of Gauss-Jordan elimination. And you'll notice that we can't even see, the way I'm displaying this, we can't even see the whole algorithm at once. It's all these steps here. And that's, just a limitation of making this video, but I actually think it highlights an important point, which is that the nice thing, one of the very nice things about this algorithm is that we don't need to be forward looking or backward looking while we're doing it. We can just focus on the thing we're working with. So we have this matrix here, and we can only look at this matrix and only look at the step we're on, and we'll know what to do. It's not important that we can look back, that we see what we previously did, and we don't have to think ahead to what we're trying to do. We just follow the process. Okay, so let's follow the process. We're going to start with row 1 as the current row. So let's emphasize that here. This is our current row, row 1. We have to identify the pivot location of the current row. So the pivot location, what is this referring to? Well, we're going to identify the leftmost column that contains a non-zero entry in the rows at or below the current row. Okay, that's everything. The rows at or below the current row is all this. And the leftmost column that contains a non-zero entry somewhere is this column. Right? So we have a 0 in this row, but there are non-zero entries below it. So this is our pivot column. So we're at the pivot row and the pivot column. That means that this is the pivot location, the top left corner. So the intersection of the current row and the pivot column. So we identified what row we're working with. We looked at the leftmost column with a non-zero entry in the rows at or below the current row. That's our pivot column. The point in the pivot row and the pivot column is the pivot location, and the entry there is the pivot. There's a lot of terminology here, but it's more important that you understand the process, and the terminology will come with time. All right, so that was step 1. It was just to figure out what are we working with. Or I guess that's step 2. Step 3, make the pivot non-zero. Okay, well, right now the pivot is 0, and so we need to make it non-zero. And when we have an action in this process, like make the pivot non-zero, any action is always accomplished with an elementary row operation. So how are we going to make the pivot non-zero? Well, if the pivot is a 0, we're going to switch the current row with another row at or below the current row that has a non-zero entry in the pivot column. All right, so we want to switch this row with another row that's below it. So we're trying to take this row and switch it with some row that's below it. And I could switch it with either of these two. I'm going to choose to switch it with the second row because I know that that'll work out nicer in this problem. But if you had chosen to switch it with the third row, it would still work. This process would be just fine. So this is going to be my first transformation of this matrix. And so we scroll down here, and now we no longer have the system in front of us, but we don't need it. We don't need to look back or forward while we're doing this process. So here what we're going to do is we're going to switch row 1 and row 2. And we'll have some shorthand notation for this that's somewhat standard, but I mean, it's not totally standard. We'll write that like R1, double arrow, R2. This is representing that we're switching those two rows. So what happens when we switch row 1 and row 2? Well, we get, I guess I could copy paste this, but I'm not going to. When we switch row 1 and row 2, we have row 2 now goes to the top. It replaces row 1. And row 1 becomes row 2. I already made a little error. It's very easy while you're, especially when you're talking while doing it, but it's very easy to make arithmetic errors in these problems, so it's really important to keep track of what you're doing. I just wrote something in the wrong spot, but here what we've done is we've switched row 1 and row 2. So that's our first step. Okay. So our next step here, we need to make the pivot equal to 1. So again, this is an action. So this is going to be something that we have to accomplish with a row operation. And so the pivot's not 1. We're going to multiply the current row by a number to make the pivot 1. Well, our pivot is -2. And so we need to multiply this by something to make it 1. So we need to multiply it by -0.5. And so again, we can hop down here. It doesn't matter what we did previously. All that matters is what we're doing now. So we're going to multiply row 1 by minus 1/2. And the way we'll write this is minus 1/2 R1, arrow R1. So this is saying we're going to take negative 1/2 row 1 and put it in place of row 1. All right, so here I will copy and paste this matrix. If I don't copy and paste, I'm going to make way too many errors. And it'll take a long time. So I'm going to copy and paste my matrix. And I need to go in, and all I'm doing is modifying row 1. Right, so when I multiply this by minus 1/2, minus 2 becomes 1. Let's actually just erase the whole thing so that we're really careful. So minus 2 becomes 1. 10 times minus 1/2 is minus 5. Minus 16 times minus 1/2 is 8. 2 times minus 1/2 is minus 1. Minus 14 times minus 1/2 is 7. I now have a pivot equal to 1. Next step. And I should be scrolling this up earlier, right? When we get to a next step, we don't worry about what we did previously. We're now working with this matrix. Make all entries below the pivot 0. This means entries directly below the pivot. Maybe I should add a word here. The nice thing about a Google Doc, I can fix my mistakes as I go. I'm talking about these entries, right? Our pivot is here. I want to make these two entries 0. Now, the first entry here is already 0, so I don't have to deal with this. I'm going to need to make that entry 0. And any action is going to be an elementary row operation. The only way to make this entry 0 is going to be by adding a multiple of our current row to that row. And so that's what we can always do. We have a 1 here, and we can add some multiple of this row to this row to make that entry 0. So what do I need to do? I need to add -3 row 1 to row 3. I'm starting to abbreviate a bit more, and soon we'll get to the point where I'm just going to write things as our shorthand notation to save time. But the idea here is that will get rid of this 3, right? Because -3 times row 1 will have a -3 here, and then when I add that to row 3, I'll cancel out that 3 and get a 0. So here my notation is row 3, or let's write it like this. I think it doesn't really matter because addition is commutative. I'll write it like this. -3 R1 plus R3, arrow R3, is saying I'm going to add -3 row 1 to row 3, and I'm going to replace row 3 with that. Again, let's copy this. Paste it. And it can be a good habit when we do this sort of thing, we're replacing all of row 3. So let's just get rid of it. If you try to replace one at a time, you can run into issues. So I'm adding -3 times this row to this row. This first entry, I start with the 3, but then I add -3 to it, and I'm going to get 0. This next entry, I'm going to be slow for this because it's important to really follow this carefully. We're going to do -3 times -5 is 15. 15 plus -19 is -4. -3 times 8 is -24. -24 plus 12 is -12. -1 times -3 is 3. 3 plus -8 is -5. And then finally, 7 times -3 is -21. -21 plus 18 is -3. It's so easy to make mistakes, so I'm trying to be really careful. All right, so all entries directly below the pivot are 0. And so we're now done with this pivot column. So So we go to here, move down a row, return to step 2. So we're going to hop down to row 2 and get ourselves another page in this document. We're going to hop down to row 2 and we're going to return to step 2. Let me actually drag this down a little bit because that will make this a bit nicer to work with. All right, so we have to return to step 2. Let's scroll back up. So again, we need to identify the pivot location in the current row. And this one is a bit more interesting than the first one, so I'll actually dwell on it more this time, because the first time all this information was worked a little differently because we didn't have to ignore stuff. So I want to identify the leftmost column that contains a non-zero entry in the rows at or below the current row. What this is saying is it's saying, look, we don't care about this top row because that's above our row. So we're going to look at just the rows at or below our current row. And what is the leftmost column with a non-zero entry? That's here. And so this is our pivot column. And that means that this is our pivot. Okay, so now we've identified the pivot. It's this 6. We have to make the pivot non-zero. It's already non-zero. It's 6. So let's make it equal to 1. How are we going to make this pivot equal to 1? We're going to multiply it, the row, by something. And so here, what we should do, and I'd recommend, as you're watching this video, there's something to be said for, sorry, my pen changed settings. There's something to be said for pausing the video occasionally and saying, all right, what's the next step? So I need to make this entry a 1. What should I do? So if you want, pause the video. So what I should do is I should multiply row 2 by negative 1/6. So minus 1/6, row 2 is going to replace row 2. Copy this, paste it, and see what we get. So we'll go in and erase the entire row 2. What happens when we multiply this thing by negative 1/6? Well, 0 times minus 1/6 is 0. Did I say minus 1/6? Yeah. This should be positive 1/6. And these are the sorts of things that if I realized I had made this mistake, because this isn't what I wanted, but it should be positive 1/6. I don't know why I said minus, because I want to turn this thing into a 1, not a negative 1. And so, all right, positive 1/6 times row 2. It doesn't actually change this, right? 0 times positive 1/6 is 0, and 6 times 1/6 is going to be 1. 18 times 1/6 is going to be 3. 12 times 1/6 is 2. And 0 times 1/6 is 0. So I made the pivot 1. Now I need to make all of the entries directly below the pivot 0. So what should I do to this thing? Well, again, pause the video if you want to try to figure out what the next step is. So what I'm going to do is I'm going to add 4 row 2 to row 3. I don't know why I started writing these things with subscripts instead of numbers. Doesn't really matter, but I was writing it like this. 4 row 2 plus row 3, replacing row 3. And the idea here is that I'm trying to get rid of this minus 4. I want to make all of the entries below the pivot equal to 0. So again, we'll copy and paste, or if you have to write this out on paper, just carefully copy everything but that third row, because that's the one that's being replaced. Now you'll notice I erased that 0, and as you get in the habit of this, you'll start to see some patterns, and you'll maybe start to see why we're doing it the way we're doing it. I erased that 0, but that's not going to matter, right? So here I'm going to add 4 times 0 plus 0 is 0. And notice, this whole column that we had previously dealt with never gets changed, and it's because of all those zeros, which is why we're doing it this way. All right. 4 times 1 is 4, plus negative 4 is 0. 4 times 3 is 12, plus negative 12 is also 0. Oh, we got another 0. We weren't even trying to do that, but that works fine. 4 times 2 is 8, plus negative 5 is 3. 4 times 0 is 0, plus negative 3 is negative 3. And you may notice that we actually now have a matrix that's in echelon form. But I want to actually finish this process. You could say that this was a place to stop if you wanted. We could probably now solve this system. But to finish the forward process, I want to just keep going through the algorithm. I want to not really think. I just want to kind of follow the steps that I'm supposed to. So now I'm working with this. And I need to move down a row. So now I'm moving down to the bottom row. And return to step 2. So I need to identify the pivot location. So I want the leftmost column that contains a non-zero entry, but only looking at the row I'm on and anything below. And so that's this column. So let's write that in. We've got our pivot column. That means that this is our pivot location. So we've identified our pivot location. It's that 3 is the pivot. The pivot is already non-zero, so we don't need to do anything there. We now need to make it equal to 1. Again, pause the video if you want to think about what we need to do to make this equal to 1. I need to multiply by a third. Hopefully get it right this time. I need to take 1/3 row 3 and replace row 3 with it. Okay, so again, now I'm going to not really skip steps here, but I'm going to point out one thing. I don't need to erase all these zeros, right? The whole point of this process, if you're getting a feel for this, is that those zeros remain unchanged, and I don't really need to rewrite them. I'm multiplying zeros by a third. That's not going to change anything. What does get changed? Well, 3 times a third is 1, and minus 3 times a third is minus 1. And so I've made the pivot equal to 1. There are no entries directly below the pivot. Did not want to do that. So I don't need to do this, right? To move down a row, well, I can't move down a row. Well, if I'm at the bottom row, then I'm done with this forward direction, right? There's 2 parts to this process. It's a long process. So now the matrix is in echelon form, right? So it has this staircase shape. As we move down into the right. So it's in echelon form, and these 3 are the pivots. These are all 1. To be in echelon form, it doesn't require these entries to be 1, right? This is also a matrix in echelon form. But this process takes us to a matrix in echelon form where all the entries are 1. And a quick thing just to point out is that it's conceivable, depending on your system, you can end up in a situation where as you work forward, you aren't at the bottom row, but everything beneath where you are just rows of zeros all the way across. And if that happens, you're also done because you're in echelon form and all the pivots are 1. All right, forward direction is completed. This video is already almost 25 minutes long, so if you're still with me, great. But a bit longer, I guess, than I estimated. Let's go and see what we do with the backward direction. So remember, our goal is to get to reduced row echelon form. We're not there. We'll explain what that means when we get there. It consists of the forward direction and the backward direction. The backward direction is again going to be a sequence of elementary row operations, but the backward direction is much more straightforward in the sense that we really just kind of work through it pretty quick. There's not going to be any row switching or anything like that. We just need to cancel out as many entries as we can and make them 0. So let's see what the backward direction looks like. And we can actually fit it all onto one screen. So in the backward direction, we're going to work bottom to top. So we have this matrix. This is where we finished our forward direction. And our current row is going to be the bottom row. If you have a bunch of zeros at the bottom, you go up to the first row that doesn't contain a bunch of zeros. So we're going to start with this bottom row. And what we want to do is we want to make all of the entries above the pivot 0. So I want to make these two entries 0. So how do I do that? Well, I got to choose one of them to make 0 first. So let's make, I don't know, let's make this one 0. So if I want to make this entry 0, think about how we're going to do that. Pause the video if you'd like. I'm going to replace row 2 with -2 row 3 plus row 2. Or in other words, I'm adding -2 times row 3 to row 2, specifically because of those two entries that I just circled, the 1 and the 2. I want to get rid of that 2. So what do we get? Well, I'm not going to go in and just erase a bunch of stuff. And so this is where we're going to start to see patterns here. Because I'm working back up and I already got rid of a ton of entries, when I add this row up, I add multiples of row 3 to row 2, all these zeros are not going to change anything above them. And so when I go in and erase stuff, I'm actually just going to erase these things. I could write it out if I wanted, but it's important. This is an important property. It explains why we're doing it the way we're doing it. These entries aren't going to get changed by adding a multiple of row 3 to that row because they're left of the pivot. And so I'm adding zeros up. So what happens here? Well, I get a 0 here, right? I get -2 times 1 is -2 plus 2 is 0. Now here, I have -1 times -2 is 2. 2 plus 0 is 2. And so I get a 2 in this entry. And so I'm done with that step. And now I need to keep making all of the entries above the pivot 0. I need to, my next step, or we can ignore what we've just done. We know where we are. I need to make this thing 0. And so I'll write it like this. 1 times row 3 plus row 1 will replace row 1. Or in other words, I'm just adding row 3 to row 1. Because if I add a 1 to a -1, I'll cancel that out. And again, this process, I can only possibly change these entries because when I add row 3 to things, these zeros don't change anything. So I only can possibly change those two entries there. What happens? Well, I'm just adding row 3 to row 1. So 1 plus -1 is 0. -1 plus 7 is 6. So I'm done with making the entries above the pivot 0. Now I need to move up a row and return to step 2. I'm going to hop up to the second row. And I'm going to make all the entries above that pivot 0. This is the pivot. I want to make this thing a 0. So I'm going to need to add 5 times row 1. Move this thing down. Paste it and see what we need to do here. I guess I need to move this up a little. I didn't quite accomplish what I wanted. Get it all on the same screen. So what I need to do here, we're working on this row again. I need to get rid of this entry, I need to add 5 row 2 to row 1. So 5 row 2 plus row 1 replaces row 1. And I'm going to erase some things and not other things. And just notice that when we do this, we can't possibly change anything left of our pivot because we have zeros left of the pivots. All right, so I don't need to worry about this. And we're not going to change this 0 because it has a 0 below it. And so what is going to get changed are these entries. So what's going to happen? Well, 5 times 1 is 5 plus negative 5 is 0. 5 times 3 is 15. 15 plus 8 is 23. If I wanted to, I could, add 5 times 0 plus 0, but that's not going to change anything. 2 times 5 is 10. 10 plus 6 is 16. And, okay, move up a row. Well, when I move up a row, I now get to the top row. There's nothing else to do, right? There's no entries above the pivot. And so I'm at the top row. The backward direction is completed. The matrix is in reduced row echelon form. All right, so what does this thing mean? What does that mean? So this is in reduced row echelon form. I don't want to have to write this a bunch, so I'll always write RREF. What makes it a matrix in reduced row echelon form? The overview gave a definition, so let's scroll down to this. Okay, so a matrix is in reduced row echelon form, first of all, if it's in echelon form, which it is, right? That we have this staircase shape to it. So it's in echelon form. The first entry in each non-zero row is a 1. Okay, so all of the rows are non-zero, but the first entry in each row is a 1. And if we had some 0 rows, rows of all zeros, that would be fine as well. They would have to be at the bottom because it's in echelon form. And above and below our pivots are all zeros. So each pivot has only zeros above and below it. That's what makes it reduced row echelon form. And so we've gotten through all of this very long converting the augmented matrix into reduced row echelon form. And now we have a matrix that we can solve very quickly. So let's write this as a system of equations. Although you'll see, if you get familiar with this, you can actually just read off of this reduced row echelon form what the solutions are. Maybe try this if you want. If you've seen this before, if you're still at this point in the video, say, all right, I'm going to try to just kind of guess or see if I know what the solutions are. Let's convert this back to a system. So this is 1x1 plus 23x3 equals 16. The second equation is 1x2, so x2, plus 3x3 equals 2. And this final equation is x4 equals minus 1. Let's solve this thing by back substitution. So again, we can move down. We can ignore what we had in the past. All right, going through back substitution, we start at the bottom. x4 is minus 1. That's easy enough. Moving along, x3 is a free variable, so we should call it something. I'll name it s, right? We have to choose some parameter to represent any free variable. Now we take this equation. So we have x2 plus 3x3 equals 2. And I'll sub in that x3 is s. So x2 is 2 minus 3s. And then finally, at my top equation, let's write this down. x1 plus 23x3 equals 16. x3 is s. So x1 plus 23s is 16. That means that x1 is 16 minus 23s. Let's write this all in a nicer format. It's always good form to be very clear about what your answers are and to, write them in a reasonable order. Here is the solution to this system. x1 is 16 minus 23s, x2 is 2 minus 3s, x3 is s, and x4 is minus 1, where s is any real number. And so we're done. We solved this thing. And hopefully I've convinced you that at no point were we guessing, right? I mean, you have to learn how this algorithm works and you have to understand it, but there's no guessing. At no point did I do something where I was unsure whether that step would lead me towards a solution. Everything I did was very intentional. And I didn't need to look forwards or backwards. That is, I only needed at any point, if I just zoom in on some matrix partway through the system, right? If I stop right here and I look at this matrix, I know, since I've done this a bunch, that my next step is going to be to get rid of this entry. I don't need to see what happened before or what happened after. And so as you get familiar with this, you'll get this feeling where you can look at a matrix, you can understand, what row are we on? I can tell what row I'm on, I can tell what column I'm working with, and I know what I need to do next. And so hopefully that's how you feel. That is, as you work through some problems, even though this might initially look intimidating, you'll realize, hey, this isn't so bad. The other thing I want to say about this algorithm is that what we'll see is that we're using it right now in the context of systems of equations, but we're going to do this all the time throughout the course. So we're going to work with matrices more generally in this course. Right now we're using this augmented matrix, augmenting referring to the fact that I have this dividing line. We're using it to represent a system of equations, but we'll use matrices just kind of on their own and also to represent other things. And when we do that, one of the things we will very often do is convert a matrix to either echelon form or reduced row echelon form by a sequence of elementary row operations. So this is something that you need to know how to do. It's not something you can get away with not knowing. And so even though this algorithm seems maybe a bit intimidating, maybe a bit complicated, putting in the time and practicing with it, you'll not only have it make more sense so that you don't necessarily need to think each time about what you're supposed to do, but it'll pay dividends in that you're going to need it over and over again. So there's a few things that I wanted to mention here at the end. One is, it's really important that when we do a sequence of elementary row operations, we only do one row operation at a time. If you do multiple row operations at the same time, you can run into a lot of trouble. It's because two operations at the same time, all of a sudden you can lose information. I'm not going to come up with an example to show you why this is true because I don't know that that's useful. But you have to be careful. When you start to do more than one thing at the same time, things can, in weird ways, cancel each other out. All right, there's one place, though, that we can get away with this. And that is, if we're adding multiples of the same row to a bunch of other rows, we can do that all at once. And so in particular, when we're making the entries below the pivot 0, we can get rid of all those entries at the same time. You have to be careful, but you can do them all at once. And similarly, in the backward direction, making all the entries above the pivot 0, you can do that all at once. And I want to show you what I mean by going to this step in the backward direction. Let's find it here. Yeah, so it's these two steps. If I wanted to, see if I can get them both on the screen, I could have done both of these at the same time. Wait, is that true? No, sorry, yeah, I need to scroll back up. It was these two. I could have done both of these at the same time. So when I had this matrix here and I'm trying to get rid of these two entries, right? I'm trying to make the entries above this pivot 0. This is what we're working with. if we're being careful, we can always just do one at a time. That's always best unless you're certain. But if I'm adding multiples of row 3 to a bunch of other rows, I can do all of that at the same time. That's the one situation, the same row to other rows. And it shows up in our algorithm, so it can be worth doing. That is to say, I could have canceled out this 2 and canceled out this -1 in one big step. So I could have hopped all the way to this matrix rather than writing out those intermediate steps. So if we want, that's the one situation where we can combine 2 row or more row operations into one kind of combined, no longer elementary row operation. There's one final thing I want to mention, because I've said that as you're doing this algorithm, you really don't need to be looking ahead or looking back, which is true. It's one of the things that can make a mathematical algorithm really nice, is when you can only work with the thing on the screen in front of you. You don't have to think about the fact that you're working with systems of equations. You don't have to think about, what did I do 2 steps ago? You just focus in the moment. What am I doing right now? You do want to always keep in mind one thing, which is that sometimes something will happen and make it very clear to you that your system of equations is inconsistent. That is, that it doesn't have any solutions. So the only thing that we're going to have on the back of our mind at all times is that maybe our system's inconsistent, and if something shows up, we should do something about that rather than wasting a bunch of time. And so let me show you what I mean. So I'm going to write down a different system. So let's get to a totally new page. So I guess this is example 2, and this will be a much quicker example. I'm trying to make it as minimal of an example as possible. So let's say I'm working with this system, x1 minus, or let's write these as x, y, and z just to mix things up. So x minus 5y plus 9z is 13, minus 3x plus 15y minus 27z is 5, and 5x plus 8y plus 7z is 0. All right, so step 1, and I'll be quick about this because I want to get to the point where something happens. Step 1, augmented matrix. So I convert this to an augmented matrix. I identify the pivot. I'm in this row and I'm in this column, so I'm currently working with this pivot. It's already 1. Right, we're in the forward direction now. And I want to make all entries below the pivot 0. And I could get rid of both of these at once, but I know I made this problem, so I know what's going to happen. I'm going to try to get rid of this entry. So I ignore the system of equations. I no longer need to think about the fact that I'm working with a system of equations. I'm going to do 3 row 1 plus row 2 in place of row 2. So that's going to get rid of this minus 3. I'm going to paste this here. And so what's going to happen? Well, so 3 times 1 is 3, plus negative 3 is 0. 3 times negative 5 is negative 15, plus 15 is 0. 3 times 9 is 27, plus negative 27 is 0. 3 times 13 is 39. 39 plus 5 is 44. And this is the one thing that you always want to keep in mind, because you can save a lot of time. Because what could I do? I could keep going. I could say, hey, I need to get rid of this 5. And I need to, continue the process. I need to find the next pivot and so forth. But I can already tell that this system doesn't have any solutions. And so this is the one thing that you do need to keep in mind. That is, you can focus on what you're doing at all steps. But anytime you see a row like this, a row where you have all zeros on the left-hand side and something non-zero on the right-hand side, you should stop. Because this row is telling us that 0 equals 44, which is not true. I don't think that's a surprise to anyone. 0 is not 44. And remember what this means when working with systems of equations. When you're doing a sequence of elementary operations and you end up with a false statement with a system of equations, the reason this happened is because you were working with them under the assumption that there was some solution that worked for everything, but it turns out that that's not the case. And so you just end up with this total nonsense. And so I can stop right away and say that there are no solutions. I don't have to complete the process of reducing this to reduced row echelon form when I already know from this line that there are no solutions. And remember, the issue is the 44, right? If this were a 0 here, that would be fine. That would be saying that 0 equals 0, which is true. And that's saying, in some sense, maybe our equations were redundant. Multiple equations together were saying the same thing as another equation. And so this is an important thing to keep in mind, that even though we have this idea that we don't need to think about what we're doing, that is, we don't need to think that we're working with systems of equations, we just need to do row operations, look for these rows, and whenever they show up, stop. Don't keep working. Maybe there's the occasional homework problem where WebWork tells you that you have to keep working, right? It makes you reduce it all the way to echelon form, but unless that's the case, stop once you know there are no solutions. All right, so I know that was a really long video. Hopefully you didn't watch the whole thing unless you really wanted a full overview of this. But if you did, thanks for staying with me for that whole time, and I hope it was useful.